Both Einstein's special theory of relativity and my supervelocity and selection theory of light are theories about the behavior of light. But both theories are also theories about space, time, velocity space, and the overall structure that determines the set of relationships that operate between these three overlapping coordinate systems. Let's focus on the behavior of light first. Implicit in the two postulates of special relativity is the idea that light must know where the observer is or will be in velocity space before it can decide on where it is in velocity space. This is obviously a naive account of the behavior of light, as it is one that is derived directly from the observations, but it has not yet been tainted by any theory. But this is also an accurate description of the apparent behavior of light, for which special relativity has been tasked with providing a coherent alternative explanation. The explanation that the proponents of special relativity have eventually settled on is the idea that light is able to coordinate its motion with the observer indirectly through interactions between space, time, and velocity space. And the overall structure of these interactions is known as Minkowski spacetime. Just as with special relativity, according to the supervelocity and selection theory of light, light does not actually know where the observer is or where the observer will be in velocity space. This makes sense because light is not the sort of thing that can either possess knowledge or make decisions. One might also wonder why it is that light would care about how fast or in which direction an observer is moving. According to the supervelocity and selection theory of light, the decision about where light should be in velocity space is not made by the light itself, nor is it made by the structure of the relationships between time, space, and velocity space. Instead, the supervelocity and selection theory of light postulates that the decision about which velocity the light should have is made by the observer by virtue of the observer's location in velocity space. So the light does not choose its own speed, and nor does any consequence of the structure of time and space. According to the supervelocity and selection theory of light, it is the observer that selects the speed of the light that they observe. As a result of their different ways of explaining the observer-dependent and observer-centered behavior of light, these two theories arrive at different positions with respect to how time, space, and velocity space are related to one another. I will now illustrate these differences with a simple thought experiment. Let's just imagine that telecommunications have not been invented yet, but we do have two friends, a clock, and a coffee shop. In scenario A, two friends arrive at the same coffee shop on a Sunday afternoon at 4 o'clock p.m., and they stay until 6 o'clock p.m. Being in the same place at the same time allows the two friends to interact and converse. Both Einstein's special theory of relativity and the supervelocity and selection theory of light are in agreement with respect to scenario A. It is indeed possible for the two friends to be both in the same place at the same time. However, in addition to sharing a location in time and in space, the two friends must also share the same location in velocity space. Scenario A is useful to demonstrate the similarities between these two theories, but the differences will become more clear once we consider Scenario B and Scenario C. Let's turn now to Scenario B. In Scenario B, there are two coffee shops and two friends. The two friends arrive at two different coffee shops separated by 2 kilometers on a Sunday afternoon at 4 o'clock p.m. and they both stay at their respective coffee shops until 6 o'clock p.m. In this case, there is no interaction between the friends because they are 2 kilometers apart. With respect to scenario B, special relativity says that two events cannot occur in two different places at the same time because simultaneity is relative to an inertial frame of reference. So the two friends may believe that they are in different coffee shops 2 kilometers apart at the same time, based on what the clocks on the walls say while they're there. But according to special relativity, the idea that the two friends are in two different places at the same time is just not true. The clocks on the walls may be ticking at exactly the same rate, but it is impossible for the two clocks to be synchronized in all possible inertial frames of reference. Simultaneity is relative to a specific inertial frame of reference according to special relativity. By contrast, according to the Supervelocity and Selection theory of light, simultaneity is absolute. Therefore, according to my theory, we can meaningfully say whether or not the two friends, who are in two different places, occupy these places at the same time. So to recap, special relativity says that the two friends cannot be in two places at the same time, but the Supervelocity and Selection theory of light says that the two friends can be in two places at the same time. Now let's turn to scenario C. Scenario C is the most complicated scenario, and this is because special relativity takes contradictory positions in this scenario. It is relatively unclear where special relativity stands. By contrast, the Supervelocity and Selection theory of light takes an unambiguous position with respect to scenario C. In scenario C, two friends arrive at the same coffee shop on a Sunday, but one friend arrives at 2 o'clock p.m. and stays until 4 o'clock p.m., while the other friend arrives at 6 o'clock p.m. and stays until 8 o'clock p.m. In this scenario, there is also no interaction between the friends because they are never at the same place at the same time. According to the Supervelocity and Selection theory of light, the two friends are not really in the same place at different times. This conclusion follows directly from the first postulate of special relativity, which says that the laws of physics are the same in all inertial frames of reference. While the two friends are both in the same coffee shop, and they both observe the same clock on the wall, we cannot say that they are ever in the same location in space. We cannot say that the two friends are in the same place because we do not know how fast or in which direction the coffee shop has been moving during this time period. We cannot assume that the coffee shop was stationary because to assume that the coffee shop is stationary is to invoke an absolute inertial frame of reference. Special relativity also says that two events cannot occur in the same place at two different times, because what counts as the same place depends on an arbitrary inertial frame of reference. The coffee shop may or may not be in the same place for both friends. The spatial coordinate system that we have been implicitly relying on also has a defined location in velocity space. If we had chosen a different location in velocity space for our spatial coordinate system, then we would have to come to a different conclusion. Not only can we not know or determine whether or not the coffee shop was in the same place, but it is also considered to be meaningless to talk about whether or not it was in the same place. It would appear as though both theories are in agreement with respect to scenario C, because we can all agree that there is no such thing as an absolute inertial frame of reference, but not so fast. Like an Ouroboros, special relativity devours its own foundations. Special relativity actually does posit the existence of an absolute frame of reference. And there are three examples of this which I will use. One is the concept of Minkowski spacetime. The second is the idea of cosmological expansion. And the third is the idea of breaking the symmetry in the twin paradox. According to the model of Minkowski spacetime, the faster one moves through space, the slower one moves through time, and vice versa. Therefore, it is implied that it is possible to move relative to space itself and that space itself occupies a defined location in velocity space. That would make space itself an absolute inertial frame of reference. Secondly, according to the standard special relativity friendly interpretation of cosmological expansion, distant galaxies move at superluminal speeds with space, but not through space. So it is the space itself that is really moving at superluminal speeds, and not the galaxies. In other words, the space itself occupies a defined location in velocity space, and it functions as an absolute inertial frame of reference. Finally, in order to resolve the twin paradox, proponents of special relativity have proposed that there must be a way to break the symmetry and to determine which twin was actually moving and which twin was actually stationary. This also implies the existence of an absolute inertial frame of reference. To reiterate, in scenario A we have two friends meeting at the same time and in the same place, and both theories agree about this. In scenario B, we have two friends meeting at the same time but in different places. Special relativity says that it doesn't make sense to say that the two friends occupy different coffee shops at the same time. But the Supervelocity and Selection theory of light says that it does make sense to say that the two friends occupy different coffee shops at the same time. In scenario C, we have two friends meeting at the same place, but at different times. Special relativity cannot make up its mind about whether or not we can say that two friends are really meeting at the same place, but the Supervelocity and Selection theory of light is clear about this. According to the Supervelocity and Selection theory of light, we really cannot say that the two friends are in the same place at different times. It is difficult to construct a model that incorporates 3 dimensions of space, 1 dimension of time, and 3 dimensions of velocity space. Time becomes a bit of a troublemaker when it is introduced into the model and combined with the idea that all inertial frames of reference are equivalent, because we end up needing to consider the interactions between time, space, and velocity space. While the 3 dimensions of space are real, the entire spatial grid must also share a single point in velocity space. In other words, any spatial coordinate system must itself have a defined location in velocity space. But velocity is also derived from an integration of both space and time. And yet, the 3 dimensions of velocity space are also just as real as the 3 dimensions of ordinary position space. In other words, every position is also a velocity, and every velocity is also a position. Is velocity space at the base of reality, or is position space at the base of reality? I will leave this question open for now because it's very difficult to answer.